This is a video lesson for friction problems. The learning target for this lesson is, I am learning to use the definitions of static and kinetic friction to solve AP style and real-world problems. The success criteria for this lesson are, I can use the equations for static and kinetic friction to solve real-world problems. And I can use mathematical reasoning with the equations for static and kinetic friction to solve AP style friction problems. So let's do a quick review of the equations for static and kinetic friction. So the magnitude or the strength of the frictional force has two forms. Static friction, when objects are touching each other but not moving, which is F sub s, which is less than or equal to mu sub s times n. And then kinetic friction, when an object is moving relative to another object, which is F sub k, is equal to mu sub k times n. So the mu, which is the U-looking thing, which is the Greek letter mu, that is the coefficient of friction. So mu sub s is the coefficient of static friction, and mu sub k is the coefficient of kinetic friction. And those are determined by experiment with the object that is doing the sliding. So a hard surface or a soft surface, a sticky surface or a smooth surface, a bumpy surface, etc. Okay, let's look at some other examples of how to solve friction problems. So, example number 1, you hold a 2 kilogram textbook against the wall with a static friction coefficient of 0.5. What is the maximum or the minimum force you must apply to the textbook for it to not slide down the wall? Okay, so as usual, we'll start with a free body diagram. Okay, so we have the force of gravity. So that's mg. So this would be the 2 kilogram textbook times g, which is 10 meters per second squared. So that gives us a force of gravity of 20 newtons. Okay, so we are pressing against the wall with a force. So we have an applied force here, which is what we're trying to figure out. And that gives us a normal force, which is balanced with that applied force. And then we have a static friction force here, which is balanced with this 20 Newton force of the gravitational force. Okay, so what we're trying to figure out then is what the normal force is. That's going to tell us how much we're going to use to apply this force. So our static friction force is less than or equal to mu sub s times n. So we want this to be equal to 20 newtons. So we're going to write our static friction force is equal to mu sub n, or mu sub s times n. So we have 20 newtons is equal to 0.5 times the normal force. So we're trying to figure out what the normal force is here. So divide both sides by 0.5, that's the static friction coefficient, and we end up with the normal force is equal to 40 newtons. So that's also equal to the force that we have to apply, because the normal force and the applied force are balanced with each other. So normal force and applied force are equal to each other. Since the applied force that you're putting on the book here, you're applying this force here, the normal force is equal to and opposite that applied force. Okay, example number 2. An 833 kilogram Formula One car experiences 25,000 newtons of downforce at a high-speed corner. If its tires have a static friction coefficient of 1.8, what is the maximum frictional force between the tires and the track? All right. So free body diagram, we have the force of gravity, which is equal to mg. So that is 833 kilograms times 10. So another way of writing G is as in newtons per kilogram. So that it's the same thing as meters per second squared, but when the kilograms divide out, you end up with newtons. So we have kilograms dividing out, and we have 8,330 newtons. So our force of gravity is 8,330 newtons, and then we have this additional force way greater than 8,300 newtons, and that is this down force. So I'm going to call this FDN for down, and that is 25,000 newtons. Okay, and then we have a balanced normal force, which is we have yet to figure out. Then we have this frictional force. This is the static friction force. We have to figure this out as well. Okay, so let's do some forces in the y direction first. So our sum forces in the y direction, we have normal force minus the down force minus the gravitational force, and all that is equal to 0 because these forces are balanced. So we know what the down force is, we know what the gravitational force is, so I'm going to move those to the right side of the equation so we can solve for the normal force. So Fn is equal to F down plus Fg. So our normal force is equal to 25,000 newtons plus 8,330 newtons. So our normal force then is equal to 33,330 newtons. So now that we have the normal force, we can figure out what our static friction force is. So this is 33,330 newtons. So our static friction force is less than or equal to mu sub s times n. So we're going to say that the static friction force is less than or equal to 1.8. Notice there's no units for the static friction coefficient. So the friction coefficients are unitless. So times 33,330 newtons. So our static friction force then is going to equal, we can round up to 60,000 newtons. It's a little shy of 60,000, but rounding it up is close enough. Okay, example number 3. A block of mass 2 kilograms is initially at rest on a horizontal surface. The block is pulled a distance of 10 meters in 3 seconds by an applied force. The coefficients of static and kinetic friction between the surface and the objects are mu sub s equals 0.45 and mu sub k equals 0.3, respectively. What is the magnitude of the applied force? Okay, so this is a problem with a few steps that we need to take here. So first thing we're going to do is draw a free body diagram. So F sub g is equal to 2 kilograms times 10 newtons per kilogram. So this is equal to 20 newtons. So nothing special going on here, just a block sitting on the ground. So we have a normal force of 20 newtons. Okay, so we have an applied force of some magnitude. We don't know what that is. And then we have a frictional force. We don't know what the frictional force is either. Now we know we have a kinetic frictional force because the block is moving. So we can figure out our frictional force here. So our friction force, kinetic friction force, is equal to mu sub k times the normal force. So that's equal to 0.3 times our normal force, which is 20 newtons. So this is equal to 6 newtons. Okay. So the first thing we need to do is figure out what the acceleration is so that we can figure out our sum of forces. So if we look at our sum of forces in the x direction, we have our applied force is in the positive direction minus our friction force, which is in the negative direction, equals mass times acceleration. So we have the friction force, we have the mass, we need the acceleration so we can find what we're looking for, which is the applied force. So we have to assume that the object is is accelerating as it moves, because otherwise, if the acceleration were 0, then we'd have a balanced force here, and it doesn't make any sense to give us the 10 meters in 3 seconds and that the block originally started at rest. So we're going to use a kinematics equation here to figure out what our acceleration is. So we're going to use the equation x equals x naught plus v x naught t plus 1/2 ax t squared. So our initial position is going to be 0. Our initial velocity is going to be 0. So our final position is 10 meters. So that's equal to 1/2 times ax times t squared, which is 3 seconds squared. So we have 10 is equal to 1/2 ax times 9 seconds squared. So divide both sides by, so let's see, multiply both sides by 2 to get rid of that 1/2. So that's going to be 20. So let's move it up here. So we have 20 is equal to 9ax. So divide both sides by 9. So our acceleration then is 2.22 meters per second squared. So in our sum of forces, we have the applied force minus our friction force of 6 newtons is equal to 2 kilograms times 2.22 meters per second squared. So we have the applied force then is equal to 4.44 plus 6. So our applied force is equal to 10.4 newtons. Okay, example number 4. In scenario 1, a block of mass m slides across a rough floor with initial speed v. The block slides a distance of d1 before coming to rest. In scenario 2, a block of mass 2m, made of the same material as the block in scenario 1, slides across the same rough floor with the same initial speed v. The block slides a distance d2 before coming to rest. How do d1 and d2 compare? So this is a classic AP question. They want to compare two different scenarios and see how whatever changes in the second scenario compares to the first scenario. Okay, so let's look at our friction situation here. So our kinetic friction is equal to mu sub k times the normal force. So for scenario 1, our normal force is going to equal mass times g. For scenario 2, our normal force is going to equal 2 mass times g. So our friction force for scenario 1 is mu sub k times mg. Our friction force for scenario 2 is mu sub k because the material that the block is made out of and the surface of the table is the same. So the coefficient of friction is going to be the same. So it should be mu sub k times 2 mg. Okay, so I've given myself a little bit more room here to work, and I've written down the kinetic friction force for scenario 1 and for scenario 2. For scenario 1, we have the kinetic friction force is mu sub k times mg, and for scenario 2, it's 2 times mu sub k times mg. So if we draw a free body diagram here, we have the force of gravity is balanced by the normal force, and then in the leftward direction, we have the force of friction, so the kinetic friction. All right, so if we do a sum of forces here, sum of forces in the x direction, we have minus the friction force is equal to mass times acceleration. So there's no force in the rightward direction, so the only force acting is the leftward direction, and it's slowing the blocks down. Okay, so if we look at scenario 1, based on the sum of forces here, we have minus mu sub k times mg, and that's equal to ma. So we can simplify this by dividing out the masses, and we have minus mu sub k times g equals a. If we look at scenario 2, we have on the left side, we have minus 2 times mu sub k times mg, and that's equal to 2m times a, since the mass is 2m. So here we simplify, divide out the 2m, and we're left with mu sub k times g equals a. So minus mu sub k times g is equal to a. All right, so the acceleration is equal for both scenario 1 and scenario 2. And since the velocity is equal for the initial speed is equal for both blocks, that means that the distance they travel is going to be the same. So our correct answer here is B. D1 is equal to D2. All right, so what have we learned in this video? We learned about using static and kinetic friction equations. We're going to find the normal force first, then use it to calculate the friction force. And we learned about using mathematical reasoning. So you're going to read the problem carefully and determine what it is asking for to be able to solve the problem successfully. All right, thanks everybody.